Do you see basic chemistry for biology?
Yeah.
Okay. That's what we're going to talk about today. And if we don't finish today, we will finish on Wednesday. So why do biologists need to understand chemistry? It's because all life is composed of matter. What is matter? It's something that has mass and occupies space. So living things are made up of molecules that are produced by chemical reactions. Reactants are in the position of yielding products. So if we have reactants A and B, they can react together and form C. C can be acted on and yield products D and E. This is what life really is. It's a collection of these reactions. Any life form, from the simplest single cells to complex organisms, is nothing but a collection of chemical reactions. So we'll start with atoms. Atoms are the smallest units of matter. The smallest thing that elements can be broken into by ordinary chemical means. So we are made of the same materials as occur in the rest of the universe. So when the universe began, we presume a big bang, the distribution of atoms was very different than today. The universe was entirely hydrogen atoms. And they formed stars, and they were fused into helium atoms. And those eventually fused into heavier atoms, such as carbon and oxygen. And these elements were released. And on the planet Earth, they became the building blocks for new molecules that occur in both living and non-living things. Now, I'd like to show you a short video which elaborates on this point.
Wow. I need to find the best way to learn math.
This worked perfectly a few minutes ago. It's not working now.
recognize every molecule of your body. The atoms that construct the molecule, trace to the crucibles that were once the centers of Hymen's star. It exploded their chemically rich guts into the galaxy, enriching pristine gas clouds with the chemistry of life. So that we're all connected to each other biologically, to the earth chemically, and to the rest of the universe atomically. That's kind of cool. That makes me smart. And I actually feel quite large. It's not that we are better than the universe. We're part of it. We're in the universe, and the universe is in us.
We're not the center of the universe. We are in it and of it, trying to figure it all out. There's so much we know, and yet so much we still don't know. We hold on tight as our little planet goes hurtling through space, around the sun, around the galaxy, around the universe. Don't forget to look up. There's so much to see, so much to know. Where do we begin?
All right, with that sort of gross overview picture of the universe and the fact that all life on Earth is composed of elements in the universe that were created as a result of the so-called Big Bang. So let's talk about the elements that we find here on Earth. A material that is made of only one type of atom is called an element. And each element is represented by a chemical symbol, most of them single letters, some of them two letters. And they're organized into a chart called the periodic table, which you see here. So there are 94 naturally occurring elements, and about 25 of these are essential for life. But there are 4 that are the most common in living things. And these 4 you need to remember: carbon, hydrogen, oxygen, and nitrogen. I remember them by the acronym CHON, C-H-O-N, CHON. And in a little later, we'll talk about why these 4 elements are so abundant in living things. We're going to take one of these little boxes from the periodic table and examine what's in it. So each box contains the atomic name. Atomic name in this case is cobalt. The chemical symbol is CO. Atomic number 27, atomic weight 58.9, and the electron configuration over on the right. So there's a lot of information in this little box, and you're going to be using it for one of your worksheets. So to reiterate, the major elements in living things are CHON. Here are their respective atomic numbers. Now, these elements make up about 95% of the mass of any organism, whether it's a single cell or a complex organism. About 95% of life is made up of CHON. There are other things, other elements in living things. You see some listed here. Most of them are metals. Chlorine, of course, is a gas, and the various atomic numbers. But these elements make up less than 1% of the total mass. And there are also elements which are called trace elements. You can see a list of them here. Again, many of them are metals, some are gases. They're present in extremely small quantities, making up less than 0.01% of the total mass. So even though they're in tiny amounts, they're necessary for life. And we'll talk about the roles of some of these in chemical reactions later. Some of the major ones, why do we need them? Well, calcium for bones and teeth, magnesium is a cofactor, talk about that later. Iron helps our blood to bind oxygen. Sulfur, copper, potassium, they're all important and essential. How do we get them into our body? By eating them. We can take supplements. Some diseases like cystic fibrosis can result in problems absorbing nutrients. You'll become a lot more familiar with that later. And here, for example, is the label off a vitamin bottle, giving supplements, naming them, and indicating their percent daily value. So atoms are composed of what? 3 particles. Now, I'm going to offer you a bit of a diversion and refer to a very old TV show before you were born, and most likely. The TV show was called WKRP in Cincinnati. It was on the air between 1978 and 1982. And this is for your information and your amusement. We'll see if this one works.
I can give you the basics of the atom in 2 minutes. You'll understand it perfectly and remember it for months.
2 minutes? You're crazy, you know that?
I can teach you about the atom in 2 minutes. Will you go back to school and finish out the year? How about it, huh? Come on, you're a betting man. How about it, Arnold?
Yeah. Yeah, okay, sure, you got it.
I got your word.
Yeah, you got my word. And 2 minutes.
We got a deal.
Yeah, we got a deal.
All right, sit down.
Okay.
There are 3 gangs on the street, right?
Yeah, 3 guys.
And this right here is territory. Now, here is a neighborhood. Got that?
Yeah.
And right in the middle of this neighborhood is a gang called the New Boys.
Yeah, the New Boys. Good name.
Okay. Out here on the outside of the neighborhood, on the edge of the neighborhood, is another gang. You know, these are real negative dudes, really negative, right?
Right.
They call themselves the elected ones.
All right. Yeah,
You got that? Really negative. They don't like nothing.
right.
Now, they all the time out here circling around the neighborhood, just circling, you know, checking out the New Boys. Now, the New Boys see this. And they get, you know, they figure there's something wrong here. So they make a deal with another gang, a gang of very happy-go-lucky guys. They call themselves the Pros. The Pros. Now, the Pros are very positive cats. See, they got all the good-looking women, right?
Yeah.
See, now the Pros and the elected ones, interesting thing, they hate each other. So much so that they keep the same number of members in the gang, just in case you did.
Right.
So if I got 10 elected ones, how many Pros do I have?
10.
All right. Now, how many gangs do I have?
3.
Name it.
The New Boys, the elected ones, and the Pro.
All right. Who's here?
The elected ones.
All right. Now, what are they? Negative?
Yeah, negative.
All right. Now, who's positive?
The pros, and you running out of time.
All right, now you see right here, the pros and the new boys, they call their hangout the nucleus. Now, see, that's a real tough word. It's Latin. I kind of think it's Swahili, and it means center.
Yeah. What is it?
It's nucleus. Say it.
Nucleus. Is that really African?
Say it.
Nucleus.
You got it?
Yeah.
All right. Give you another Swahili word. It's a tron. Means do.
Yeah. Tron. Do.
All these games like that name so well that they all decide to use it. For instance, the pros right here in the middle start calling themselves protons. And the new boys, well, they start calling themselves neutrons. And out here on the edge here, the electric ones, they start calling themselves the electrons.
The electrons, the protons, and the neutrons.
And all this right here, this is the neighborhood. This is block after block, nothing. You understand block after block, nothing.
Yeah. Yeah, I know all about that. And your time is up, Professor BJ.
Good. I was finished anyway. Now you going back to school.
School. Man, all I know about is a bunch of damn gangs that live in a round neighborhood.
Arnold, that's the atom. That's it, man. That's it. What's this right here?
Protons and neutrons.
All right, and they call this the what?
Nucleus.
All right, what are these guys up here?
Electrons.
Are they negative or positive?
Negative.
And how do they move?
Round and round.
And if I got two of them, how many protons do I have? Two. Now, protons negative or positive?
Positive.
All right, and what's all this right here?
Oh, that's the neighborhood.
Which is?
Nothing.
You got it, man. You get an A.
So now you know about WKRP in Cincinnati, and maybe a little bit of an introduction to an atom. So let's take it further. As you saw in the video, an atom is composed of 3 small particles, protons, neutrons, and electrons, arranged in the configuration that you see here. And there's an interesting analogy between the structure of an atom and the structure of a solar system. In this case, our solar system. So what we have in an atom is the nucleus and electrons circling around it. And these electrons are held in orbits, also called shells. And there are counterbalancing forces that keep them in their orbits. So on the one hand, they have a gravitational attraction to the nucleus. Electrons are negative, nucleus is positive. So they have this attraction. And on the other hand, they're circling, which creates a centrifugal force, which throws them away from the nucleus. So it's the balance between the centrifugal force and the attraction to the nucleus that keeps them in their orbits. And that is the same combination of forces that keeps planets in their orbits. So why does the Earth stay 3 orbits away from the sun and never deviates from that? It's because it's attracted by gravity on the one hand to the sun, and on the other hand, it's thrown away from the sun by the centrifugal force of it spinning around. So let's talk in more detail about protons. They have a positive charge. The number of protons determines the type of atom. And that is always given on the periodic table by the atomic number. So the atomic number here, 27 for cobalt, is the number of protons that cobalt has. So other elements have different atomic numbers because they have different numbers of protons. And it's the balance, in a balanced atom, the number of protons is also equal to the number of electrons, just like the guy in the video said, protons equal number of electrons, and very often they equal the number of neutrons, but not always. Let's talk about neutrons. They don't have any electrical charge at all. And they are found in the nucleus along with the protons. The number of protons plus the number of neutrons is the atomic mass or the atomic weight. So here, in the case of cobalt, the atomic weight is 58.9. Now, electrons are so small, they don't contribute to the atomic weight, even though they do carry a charge. So the atomic mass, if you want to know the number of neutrons, the number of neutrons is equal to the number of protons, the mass minus the number of protons. So you'll be doing this calculation on one of your worksheets. So for example, for cobalt, the atomic weight is 59 minus the number of protons, which is given here as 27. That equals a number of neutrons, which would be 32. So is that clear to everybody? You get the number of protons from the atomic number. You get the number of electrons because it's the same as the number of protons. And you get the number of neutrons by subtracting the number of protons from the atomic weight. And you'll have practice doing this exercise when you do the worksheet. Now, finally, electrons. The number of electrons is equal to the number of protons. The electrons circle in orbits or shells around the nucleus. And then there are isotopes. An isotope, and you should remember the definition of this, an isotope has the same number of protons and electrons, but has a different number of neutrons. So for example, carbon, normally most carbon atoms have 12 protons, or excuse me, protons and 12 neutrons. In carbon 13, there are 12 protons and 13 neutrons. In the case of carbon 14, the number of protons is the same, 12, number of neutrons is 14. There are other atoms that have similar altered numbers of neutrons. Okay, so how many electrons do we find in an orbital or a shell? Well, the first shell always has 2. The second shell always has 8. And the third shell also usually has 8, but not always. And an important point to remember here is that the most stable condition for an atom is when its outermost shell is full. So atoms that have full outer shells are non-reactive, and we'll talk about that.
I have a question.
Yeah.
So for the third, what's it called? For the ring, how many electrons can it hold?
The third, usually, excuse me, usually 8.
As well?
But there are circumstances when it.
I mean, I'm sorry. Yeah, is it the third one?
Well, this
two?
shows two orbitals. The first one has 2 and the second one has 8.
Yeah, and the third, and if it needs a fourth, is it also 8?
Could be, but the outer more orbitals have variable numbers of electrons. And for our purposes in biology, we're going to talk about 8 in the
Okay.
third orbital.
Okay, perfect. Thank you.
So these outermost, the electrons and the outermost shell are called valence electrons. They're the ones that are in contact with the rest of the world. And their number and position largely determines the chemical behavior of the atom. So here you see 3 examples of atoms that have their outermost shell unfilled, and they're very reactive. So one is hydrogen. The outer shell would like to have 2, hydrogen only has 1. In the case of carbon, its outer shell, it's a second shell, has 4, and it would like to have 8, so it's missing 4. Very reactive. Sodium is extremely reactive because it has an outer shell that it would like to have 8, and it's only got 1. So it would really like to either grab 7 from somewhere else or get rid of 1. And we'll talk about that in a minute. Now, if the outermost electron shell is filled, we have an inert element. So in the case of helium, there are 2, it only has 1 orbital, it has 2 electrons, so it's happy, it's full. Neon has 8, and argon also has 8 in its third orbital. So all of these are inert gases, and we won't deal with them in biology because they are inert. So atoms in living systems, we talked earlier about the fact that most of the mass of an organism is made up of 4 elements: carbon, hydrogen, oxygen, and nitrogen, CHON, CHON. Why is this? It's because of these valence electrons. So here you have them, hydrogen, carbon, nitrogen, and oxygen, showing their valence electrons in dark blue. It's always the ones in the outermost shell that are the valence ones. So these valence electrons can be donated. So for any given atom, it can either donate its valence electrons to another atom, or it can receive electrons from another atom, or it can share its valence electrons with other atoms. And when any of these things happens, a bond is formed. So atoms can form bonds with other atoms. And when bonds are formed, they make the chemical compounds that are found in living things. Now, in biology, we're mostly concerned about 3 different types of bonds. We'll talk about some others when we get into more specialized topics. But for right now, we're going to talk about ionic bonds, which are very strong. Opposite charges attract. So when you think of ionic, think of attracting. There are covalent bonds where atoms are shared. These are very strong bonds, even stronger than ionic. And then there are hydrogen bonds. which are caused by electrostatic attractions. And we'll talk a lot more about hydrogen bonding, and they are weak. And it's important that they're weak, and you'll see why in a little bit. So if we talk about a covalent bond where electrons are shared, if you take two hydrogen atoms, each of which has only one valence electron, they're very highly reactive. If they share with each other, they now form a hydrogen molecule, which is happy. It's not reactive. Let's talk about how ionic bonds are formed. An ionic bond forms when an electron is transferred from one atom to another. And when that happens, the donor, it becomes a positive ion. The recipient gains an electron and therefore becomes a negative ion. So now there are two ions where there were formerly two atoms. There are now two ions, one positive and one negative. They attract each other, forming an ionic bond. And ionic bonds form usually when an atom's outermost orbital contains just one or two electrons. A good way to illustrate an ionic bond is with salt, sodium chloride. A sodium atom has just one electron in its outermost shell. So one valence electron. A chlorine atom has 7. So it's missing one. And it's very reactive because it's trying to gain an electron. So what happens is sodium gives up its electron to the chlorine atom. And now because it's lost the negative charge, it becomes a positive ion. And since chlorine now has gained a negative charge, it's gained an electron, it becomes a negative ion. And these two ions attract each other, forming what we call an ionic bond. And this is another illustration of the same thing. Sodium gives up an electron, chlorine gains it. One becomes a cation plus, anion minus. They attract each other and form a molecule. Here you see a crystal illustration of a crystal of salt. Sodium ions ionically bonded to chlorine ions. Now let's consider covalent bonds. This is where we share electrons. Covalent bonds involve two atoms that share electrons. So in this case, we're going to talk about, again, two hydrogen atoms, each with one electron. If they share them, they become a hydrogen molecule. There can be double covalent bonds. So for example, in the case of oxygen, which has 6 valence electrons, it would like to, each one would like to share 2. So between the two atoms, they share 4. And this is represented in one of two ways, either O subscript 2 or O double bar O. An oxygen molecule is O2, has a double covalent bond. A nitrogen molecule, N2, has a triple covalent bond. So you've seen oxygen already, or two oxygen molecules. Each one contributes or shares 2 of its electrons. So in total, 4 are shared. This then is a double covalent bond, And it can be represented either as O double bar O or as O subscript 2. Nitrogen, on the other hand, each atom has 3 valence electrons, and it would like to share with 3 more so that each one now has 8 in its outer electron shell. And this then is represented by either N triple bar N or N subscript 2. I've circled the words molecular formula and structural formula here because it's important to know the difference between the two and how to represent them. So in the case of hydrogen, it's H subscript 2 or H bar H. Oxygen is O2 or O double bond O. In the structural formula, the molecular formula of a more complicated molecule like methane is CH4. Or if you illustrate it as a structural formula, it's C with 4 bars, 1 to each hydrogen atom. Water, on the other hand, can be represented as H2O or structurally, as you see here. So to reiterate the point, the molecular formula is the actual number of atoms of the elements in a molecule. So in the case of methane, the molecular formula is CH4. In case of glucose, it's C6H12O6. An empirical formula is the simplest ratio of the number of elements in a compound. And so you divide, to get the empirical formula, you divide the molecular formula by the lowest common denominator. So for example, in the case of glucose, the lowest common denominator is 6. So if you divide by 6, you get CH2O, starting with C6H12O6. That's the empirical formula. It's not one that's used often in biology, but the molecular formulas and structural formulas are. And again, at the bottom, the structural formula for hydrogen is H bond H or H2. Methane is CH4, or you can draw it out. Glucose, you can draw out the whole molecule. But structural formulas show the chemical bonds. Molecular formulas don't show bonds, they just show numbers of atoms. So keep those two items straight, the molecular formula and the structural formula. In writing chemical formulas, the number that is subscripted is the number of atoms. So oxygen is O2, that means there's 2 oxygen atoms. Methane is CH4, that means there's 1 carbon, 4 hydrogens. Water is H2O, that means there's 1 oxygen, 2 hydrogens. Glucose is C6H12O6, means there's 6 oxygens, 6 carbons, and 12 hydrogens. So the subscript equals the number of atoms. And if there's no subscript, the number is 1. Now the number preceding is the number of molecules. So we're contrasting the number of atoms with the number of molecules. So the top group here is a reiteration of the 4 molecules on the previous slide. And at the bottom, you can see both the number of atoms and the number of molecules. So 3CH4 means that there are 4 hydrogens and 1 carbon, making up a molecule, but there are 3 molecules. Similarly, 12 H2O means that there are 12 water molecules and 7 glucose molecules. Now, we need to talk about polar and nonpolar covalent bonds, because we're getting closer and closer to what's really important in biology. When electrons are shared equally between atoms, the molecule is nonpolar. But when electrons are skewed to one side of a molecule, it's polar. At the top here, you see a polar covalent bond, that's water. It's negative on one side and positive on the other. Methane is nonpolar, and oxygen, a molecule of oxygen, is nonpolar. You see that both of these illustrated at the bottom here. Nonpolar, the electronegativity is equally distributed. In a polar covalent bond, it's not equal. And in an ionic bond, you have 2 ions. So this is a water molecule. The big circle is oxygen with its 2 orbitals and its valence electrons. The 2 small circles are water molecules, or excuse me, hydrogen molecules, and they make up together a water molecule. Now, oxygen, by its very nature, is electronegative. So that means that its electrons are always skewed to one side. And when a hydrogen atom comes in contact, because the side that it faces is electronegative, its electrons, the side it faces are on the positive side of the oxygen, its electrons go there. And so this side becomes positive in both of the hydrogen atoms. So is that clear? Oxygen, because oxygen is electronegative on one side, it makes the hydrogen atoms positive. So that's what is meant by the atoms, or the electrons being skewed. So some atoms are more electronegative than others. Oxygen, nitrogen, and chlorine are all electronegative. Water is a polar compound. We're going to talk a lot about water now because it is such an unusual molecule. So this illustrates or reiterates what I've just been saying, that this big orange ball is an oxygen atom. It's electronegative, which means it keeps its electrons tend to be on one side of the atom. That makes the other side positive. And so hydrogen atoms, being electronegative, are attracted to that. So this leads us to a consideration of what is a hydrogen bond. Hydrogen bonds are critical in biology, and you'll see why. But what is it? It's an electrostatic attraction between a hydrogen atom in one polar molecule, for example, water, and an electronegative atom in another molecule. So a hydrogen bond is always a bond between a hydrogen atom and another atom, which is electronegative. Because oxygen, nitrogen, and hydrogen are very abundant in biological systems, hydrogen bonds are very common. So as I said earlier, hydrogen bonds are weaker than covalent and ionic bonds. And this is important because they're easily formed and they're easily broken. They're essential for life for a lot of reasons. I've got several of them listed here. The DNA double helix would be impossible without hydrogen bonds. Enzymatic activity would be impossible without them because the proteins need to be folded just right in order for them to have enzymatic activity. And the folding is dependent on hydrogen bonding. And here's an interesting note: a specific heat of water is high because of hydrogen bonding. Without it, water would boil at 80 centigrade instead of 100, and oceans and lakes would boil away, evaporate, and they wouldn't be possible on this planet without hydrogen bonding. Now, this is the way a hydrogen bond is usually represented, as a dotted line. Well, here you have two water molecules showing the electronegative side and the electropositive side. And this hydrogen bond is following the definition of a hydrogen bond. It's between a hydrogen atom and electronegative atom, in this case, oxygen. Now, multiple hydrogen bonds form wherever it's possible. So here you see a group of water molecules. If you look at the one in the middle, it has a hydrogen atom on one side, and this hydrogen atom is hydrogen bonded to the oxygen atom of another water molecule. The oxygen atom of this is hydrogen bonded to water, oxygen, excuse me, to the hydrogen of another water molecule. And here's another case, and a case of hydrogen and oxygen. So you see that these hydrogen bonds form wherever they can, wherever there's a hydrogen that can bond to an electronegative atom. So whenever there's a group of water molecules, they're usually going to be hydrogen bonded to each other, like this. This is more complex, and if you study this, you'll see that every hydrogen atom is hydrogen bonded to an oxygen atom, and vice versa. And this can get very complicated. So for example, here, and this hydrogen bonding explains why water has various forms. Like, you know that water can be solid, liquid, or gas. And if it's solid, it's ice. If it's gas, it's steam. If it's ice, it means that every water molecule is hydrogen bonded to other water molecules. So it's a network. All hydrogen bonds are formed wherever possible. Now, if the temperature is raised so that the water is liquid, it means that hydrogen bonds are forming and breaking regularly. And at any point in time, only some of the hydrogen bonds are formed. In another case, water molecules are free. In the case of gas, the temperature is raised further and all the hydrogen bonds are broken. So in gas, all the water molecules are free. So properties of water. Water is a unique chemical, and it's unique because of the hydrogen bonding. And it's because of this uniqueness of water that life exists on Earth. It's abundant both on Earth and other places in the universe. Water can be found. And its special properties are due to hydrogen bonding. 75% of the Earth's surface is covered with water. Cells are up to 95% water. It's the only substance on Earth that is found naturally in all three states, solid, liquid, and gas. It has a neutral pH, that is, it's neither an acid nor a base. And it is a universal solvent. It dissolves more substances than any other liquid. And it has a high specific heat, which means that it absorbs a lot of heat without itself changing temperature. So it's like a coolant. So, and it's this combination of unique properties of water explains why exobiologists assume that life on any planet would require liquid water. And that pretty much determines the Goldilocks conditions that exobiologists are looking for. To reiterate, high specific heat, solid phase is less dense than the liquid phase, has solvent properties, and we'll talk a little more about adhesion and cohesion. So high specific heat, that means that the amount of heat energy required to raise the temperature of 1 gram of that substance by 1 degree. That is the definition of specific heat. It takes a relatively large amount of heat because much of the heat is used to break the hydrogen bonds that hold the liquid together. So the one reason it's important that so much of the Earth's surfaces is covered with water is that it acts like a thermostat and it moderates the daily temperature changes. So if you think about it, when you go to the desert, it can be very hot in the day and very cold at night. Whereas on the seashore, you don't have this extreme range of temperature changes because the water is modulating the heat. Now, the density of water is less dense as a solid than as a liquid. It floats. It's the only case we have of that where a solid form of a substance floats, that does not float. Put it another way, for most substances, if they have solid and liquid forms, the solid form sinks. In the case of water, it floats. And that's because of hydrogen bonding. It's water molecules are fully bonded in ice, only partially bonded in water. And what would happen if this were not the case? Well, if you look at this picture of, looks like a mountain lake, the air temperature is below 0. Ice on the lake is 0. The temperature is equal to 0. And the water is warmer than 0. It's not frozen. So the ice serves as insulation between the air and the water. And the deeper you go in the lake, the warmer is the water. If this were not the case, if like most solids, it would sink to the bottom, oceans would fill up with ice and there'd be no opportunity for aquatic life. Let's talk about what happens when something dissolves in water. Again, we'll use salt as an example, case of sodium chloride. Water is polar and forms hydrogen bonds and makes water sort of a universal solvent. Before focusing on this last point, let's look at what happens when you pour salt into a beaker of water. So salt is a crystal, and you can see the green balls here are chloride ions. the blue balls are sodium ions, and they're all hydrogen bond, or they're all ionically bonded to each other. In the presence of water, the water molecules are the negative sides of water molecules are attracted to the positive sodium ions, and the negative sides are, the positive sides are attracted to the negative chlorine ions. And so you see, as you go down the picture here, by the time you get to the bottom, every chlorine atom is completely surrounded by water molecules, and every sodium atom also is completely surrounded. But for each, it's a different side of the water molecule that is facing the atom in question. So we go from having undissolved sodium crystal held together by ionic bonds, and then we have the atoms completely separated from each other when they dissolve by the water molecules. Now, interestingly, this attraction of water molecules to sodium ions and to chlorine atoms, it's neither a hydrogen bond, nor a covalent bond, nor an ionic bond. Rather, it's called an ion dipole force. So the important point to make here is that when something dissolves, there's no bonding in the chemical sense of the term, but there is a force called the ion dipole force, which allows for each atom to be separated from all the other atoms. Heat of vaporization. It's the amount of heat a liquid must absorb to convert 1 gram of liquid to 1 gram of gas. It takes a lot of heat to change water from its liquid state to its gaseous state, which is evaporation. So when you sweat, as Andre Agassi is doing here, playing tennis, it cools you down. The heat of vaporization, reiterating what we just said, why we sweat, is because of the heat of vaporization. That's what keeps our skin cool. It also keeps the surface of leaf surfaces of plants cool. And that brings us to another point to make, 2 more words for you to remember with respect to water: cohesion and adhesion. Cohesion is the tendency of water molecules to stick to each other due to hydrogen bonding. Adhesion is the tendency of water molecules to stick to other surfaces. And both of these phenomena are illustrated by what happens in a plant. Plants have their roots in the soil where there is water, and then they grow, and many plants grow very tall. And much of this is due to hydrogen bonding. So if you look at what happens in a root, water enters the root, goes into a tube called a xylem. Here you see in the stem, you see 2 tubes. And what happens here is adhesion. So the water molecules stick to the walls of the xylem more than they stick to each other, which causes them to move up. So if you think about when you drink a soda or a glass of water with a straw, and you look at the liquid in the straw, the edges near the edge of the straw are higher than in the middle, and that's due to adhesion. Then if we go higher, in the plant to the leaves, we see that there are little openings called stoma in the leaves. And that's where water molecules escape. So as they escape through the stoma, as one water molecule goes, the cohesion force drags other molecules along so that you get this steady flow of water starting with the roots through adhesion and the xylem vessels, the tubes, and then through cohesion out through the stomates. So in any given plant, there is a constant flow of water from the roots, stems, up to the leaves, and then out into the atmosphere. And all of this is dependent on hydrogen bonding. This is just a point I wanted to make about other ways you see the effect of surface tension. For example, a water strider, a bug can literally walk on water. It's because of the surface tension of the surface of the water. And the reason that some plants can grow very tall is, again, because of adhesion and cohesion inside the plant body, inside the roots, the stems, and the leaves. A life is carbon-based. And the main reason is that carbon atoms have 4 valence electrons. And so they're either wanting to give up 4, or acquire 4, or share 4. So it can bond with other carbon atoms and with other elements to make a wide variety of molecular structures. There's a whole branch of chemistry called organic chemistry. Organic chemistry deals with materials that contain carbon. Carbon in covalent bonds. And now here's something that's not directly relevant to this topic, but I didn't know where else to put it, and it's something that I wanted to draw to your attention in this course. And that is pH. You need to know what pH is, because throughout biology, pH is an important factor. So what is pH? It's the hydrogen ion concentration. It's as simple as that. It's the concentration of hydrogen ions. And in biological systems, it ranges between 1 and 10 to the minus 14th gram equivalents of hydrogen ions per liter. So something very acid would be 1, something very basic would be 10 to the minus 14th gram equivalents of hydrogen. So pH is always represented as an exponent of 10. The numbers range from 0 to 14. So pH 0 is 10 to the power 0, which is 1. That's 1 gram equivalent of hydrogen per liter. That's a pH of 0 is highly acid. A pH of 14, the exponent is 14, so 10 to the minus 14th gram equivalents, which is a very low hydrogen ion concentration. So that is a base. And this diagram illustrates how you might encounter things of varying pH in the environment or in biology. So a pH of 0, very acid, for example, hydrochloric acid has a pH of 0. Now we'll look later at the pH of the stomach. It's very acid, pH between 1 and 2. And we'll talk about why the stomach has such a low pH. Lemons, pH 2, vinegar 3, apples 4, tomatoes, bananas 5. Milk is almost neutral. Pure water is neutral. Blood is slightly alkaline. Baking soda, broccoli is alkaline. Soap is even more so, and bleach. And by the time we get to drain cleaner, which is mostly sodium hydroxide, it's pH of 14. So I think that's the last point I wanted to make today. Yes. So are there any comments or questions about chemistry for biology? Atomic structure, we went from the atoms to bonds to molecules, and finally to a special kind of bonding, hydrogen bonds, which are important for life on this planet for a lot of different reasons. And we'll talk about more of those reasons later in the semester. All right, that's all I have for today. If you don't have any questions or comments, I'll stop. We're out of time anyway. And on Wednesday, we'll talk about organic molecules. Okay. I'm going to end the show now.
Thanks, Professor.
Okay.
Thank you.
Thank you, Professor.
Thank you.
All right. I will see you all on Wednesday.